At 3:45 in the afternoon on August 12, 2026, a low-level eruption of lava that had been building for hours at the summit of Kilauea transitioned into something more dramatic. The north vent inside Halemaʻumaʻu crater, the wide collapse pit at the center of Kilauea's summit caldera, began producing lava fountains. They climbed. By the time episode 53 reached its peak, the north vent was launching molten rock approximately 500 feet, 150 meters, above the crater floor. A column of volcanic gas and fine tephra rose with it. The eruption lasted 9.6 hours and ended abruptly at 1:23 in the morning on August 13th. And here is what makes this episode not just a spectacular volcanic display, but a signal about something genuinely unusual happening inside one of the most closely watched volcanic systems on Earth. A third vent opened during episode 53. Not the north vent that has been active since the eruption began in December 2024. Not the south vent that has been its companion for months. A new west vent produced precursory overflows and emitted intermittent flames through most of the eruption. Kilauea is not just continuing the eruption that began last year. It is evolving it. New pathways for magma are opening. And as of this morning, August 22nd, 2026, the USGS Hawaiian Volcano Observatory has forecast that episode 54 is likely between August 24th and August 28th. The next eruption at America's most active volcano could begin in as few as 2 days. To understand why this eruption pattern is drawing so much scientific attention, you first need to understand what Kilauea is and why calling it America's most dangerous volcano requires careful qualification. By raw destructive power, Kilauea is not the most explosive volcanic system in the United States. Mount St. Helens in Washington demonstrated in 1980 what a lateral blast from a stratovolcano looks like, and the Cascade Range in Alaska carry several. Volcanoes capable of far more explosive eruptions than anything Kilauea typically produces. But danger is not only measured in explosion radius or ash cloud height. It is also measured in proximity to population centers, duration of ongoing hazards, and the capacity of a volcanic system to produce sustained, continuously evolving threats that force community adaptation over years rather than days. By those metrics, Kilauea's combination of continuous activity, proximity to tens of thousands of residents on the Big Island of Hawaiʻi, and the systemic threat posed by volcanic gas emissions makes it uniquely challenging among American volcanoes, and the eruption pattern it has established since December 23rd. 2024 is unlike anything the observatory has documented at this volcano in the modern monitoring era. The eruption that began on December 23rd, 2024 is characterized by episodic lava fountaining separated by pauses that can last anywhere from days to more than 3 weeks. Each episode begins with an inflation cycle during which magma refills the shallow reservoir beneath the summit, pushing the ground surface upward by measurable amounts, tracked by tiltmeters installed around the caldera rim. The tiltmeters record this inflation in units called microradians, tiny fractions of a degree of ground tilt that accumulate as the rock above the magma reservoir bends upward under pressure. When the inflation reaches a threshold, the magma finds its path to the surface through the vent system, and an episode begins. The fountain depletes the shallow reservoir. The ground deflates, and the cycle begins again. That inflate, deflate, inflate pattern, tracked in real time by the tiltmeter network, is what allows the observatory to forecast eruption windows days in advance with reasonable accuracy. The HVO has used inflation model outputs to predict episode 52 and episode 53 within narrow windows before they occurred, and the current forecast placing episode 54 between August 24th and August 28th is built on the same modeling framework applied to the tiltmeter data currently streaming from the summit instruments. What makes the current situation scientifically significant beyond the ongoing nature of the eruption itself is the opening of the west vent during episode 53. The emergence of a new eruptive vent at a location that was not previously active is not a trivial development in volcanic system dynamics. It suggests that the plumbing network through which magma rises from the shallow summit reservoir to the surface is expanding, finding new pathways through the fractured rock of the crater floor and walls. In volcanic systems that have been erupting episodically for an extended period, the opening of new vents can reflect several distinct processes. It can indicate that the existing vent pathways have been partially sealed by cooled lava or volcanic gas condensates, forcing magma to find alternative routes. It can indicate that the pressure within the magmatic system has increased sufficiently to fracture previously intact rock and open entirely new conduits. It can also indicate that the geometry of the shallow magma reservoir itself is changing, expanding laterally or connecting with previously isolated pockets of melt that create new pressure gradients pointing toward different surface locations. Determining which of these processes is dominant at Kilauea right now requires the kind of detailed geophysical analysis that the observatory conducts in the days following each episode, comparing tiltmeter deflation patterns, seismic tremor character, lava flow volumes, and gas flux measurements to build a picture of what the subsurface plumbing was doing during the eruption. The Southwest Rift Zone earthquake swarm that occurred on the morning of August 11th, 2026, just one day before episode 53 began, adds another layer to this picture. The USGS reported that 18 small earthquakes were recorded in the Southwest Rift Zone between 4 hour and 6:20 in the morning on August 11th. The Southwest Rift Zone is one of two major structural weaknesses that extend from Kilauea's summit to the southeast and southwest, forming pathways that magma has historically used to reach lower elevations and eventually the coastline during major rift zone eruption events. The 2018 eruption, which was the most destructive in Kilauea's recent history, began as a summit collapse and then migrated into the East Rift Zone, eventually producing massive lava flows in the lower East Rift Zone that destroyed more than 700 homes and buried entire communities under tens of feet of solidified lava. The hazard that Kilauea poses to residents of the Big Island is therefore not primarily defined by what is happening at the summit crater, which is remote and inaccessible to the public. It is defined by the potential for eruptions to migrate out of the summit into the rift zones and produce surface lava flows that move through populated areas toward the sea. The August 11th Southwest Rift Zone swarm did not escalate into a rift zone intrusion or eruption. The HVO reported that seismicity returned to normal background levels after the swarm ended, but the occurrence of an earthquake swarm in the Southwest Rift Zone in the days immediately preceding a new summit fountaining episode, combined with the opening of a new west vent during that episode, creates a pattern that scientists watch carefully because it could reflect the early stages of magma redistribution within the broader volcanic system. When magma fills the summit reservoir beyond a certain level, pressure within the system can transmit outward into the rift zones, generating small earthquakes as the rock fractures and adjusts to the increased fluid pressure. Whether this represents a simple pressure response or the beginning of a more significant shift in where Kilauea's eruptive activity is concentrated is one of the questions the observatory is actively evaluating. The gas hazard from the current eruption is the most immediate and directly measurable threat to the tens of thousands of residents who live downwind of Kilauea's summit. Volcanic eruptions at Kilauea produce enormous quantities of sulfur dioxide gas, which reacts with atmospheric oxygen, water vapor, and other chemicals to form volcanic smog known as VOG. VOG is a mixture of sulfur dioxide, sulfate aerosols, and other compounds that can reach dangerous concentrations downwind of the eruption and has documented health effects, including respiratory irritation, exacerbation of asthma, headaches, and more severe effects in sensitive individuals, including children, the elderly, and people with pre-existing cardiorespiratory conditions. During periods of active lava fountaining, the sulfur dioxide emission rates measured by the observatory's monitoring instruments can reach thousands to tens of thousands of tons per day, levels that drive VOG concentrations across the entire Big Island and occasionally reach the other Hawaiian islands under certain wind conditions. The gas emissions continue even during the pauses between episodes, though at lower rates, because the open vent system continues to degas the shallow magma reservoir even when lava is not actively erupting at the surface. The character of episode 53 itself contains several data points that the scientific community will be analyzing in the coming weeks to refine their understanding of where this eruption is headed. The maximum lava fountain height of approximately 500 feet or 150 meters from the north vent during episode 53 is consistent with the scale of previous episodes in this sequence, but the south vent's behavior during episode 53 was different from earlier episodes. The south vent never produced fountaining during episode 53, producing only overflows before the fountaining episode at the north vent began and then going quiet. The changing relationship between the north and south vents within individual episodes reflects how the shallow conduit system connecting the reservoir to each vent is evolving over time. If the south vent's conduit is becoming more restricted relative to the north vent's conduit, that asymmetry suggests the plumbing beneath Halemaʻumaʻu is not static. It is changing between episodes in ways that alter the distribution of eruptive output. The total duration of the episodic eruption since it began on December 23, 2024, now spans more than 20 months of continuous volcanic activity with 53 episodes of lava fountaining completed. That sustained duration at elevated eruptive intensity is remarkable in the context of Kilauea's modern documented history. The eruption that began on the East Rift Zone in 1983 and continued until 2018, producing the Pu'u's OO eruption sequence, was the longest and largest eruption in Kilauea's recorded history up to that point, lasting 35 years. The current summit eruption is clearly a different type of event, concentrated at the summit rather than distributed along a rift zone, But its episodic character and sustained duration raise questions about what is driving such persistent eruptive behavior and whether the underlying magmatic supply rate to Kilauea's shallow system has changed relative to prior periods of the volcano's activity. Kilauea sits above the Hawaiian hotspot, a zone of anomalously hot mantle material that produces a continuous supply of magma rising from great depth through the lithosphere and feeding the volcanic edifices of the Hawaiian island chain. The hotspot is fixed relative to the slowly moving Pacific plate, and as the plate moves northwestward over the hotspot, older volcanic islands are carried away from the active magma supply while new volcanic activity builds at the current hotspot location. Kilauea and neighboring Mauna Loa are the youngest, and most active volcanoes in the chain, positioned directly over the hotspot and receiving a continuous supply of magma from the mantle plume below. The rate at which magma is supplied to Kilauea's shallow system from below and the rate at which it is erupted at the surface or stored within the volcanic edifice determines the long-term behavior of the eruption. When supply exceeds eruption rate, the system pressurizes and the eruption intensifies or expands. When eruption rate exceeds supply, the system deflates and the eruption may pause or end. The fact that the current eruption has sustained itself for more than 20 months of episodic activity without transitioning to a different mode or ending entirely suggests that the magma supply rate from the deep system has remained elevated relative to what would be needed to simply maintain the status quo. Every episode of lava fountaining depletes the shallow reservoir by some amount, measured in the deflation of the summit that the tiltmeters record during each episode. The inflation that follows each episode, as the shallow reservoir refills from the deeper supply, must be sufficient to restore the pressure to the threshold needed to initiate the next episode. The fact that the system has refilled sufficiently to produce 53 consecutive episodes over 20 months implies a supply rate that is sustaining the episodic cycle rather than allowing it to wind down. The most recent HVO update as of August 22, 2026 shows that summit tiltmeters are recording deflation, continuing following the pattern of deflationary steps observed before previous episodes. Glow was observed from the north and west vents overnight. The west vent that opened during episode 53 is therefore still active in some form even during the inter-episode pause, which is significant because it means the new pathway to the surface that episode 53 opened has not been sealed by cooling lava or gas condensates since the episode ended. That persistence of west vent activity suggests the new conduit may remain active in episode 54, potentially producing a 3-vent fountaining episode for the first time in this eruption sequence. The HVO's monitoring network status itself is worth noting because it provides context for the confidence level of current assessments. HVO's monitoring network is mostly recovered from recent power and storm-related outages, with several summit stations remaining offline as technicians continue working to repair instruments and reestablish connections. The outages that affected summit stations, caused by a combination of power disruptions and storm impacts at the summit elevation, temporarily reduced the observatory's real-time data stream from the instruments that provide the most detailed view of what is happening beneath the caldera. The partial restoration of the network means that the current tiltmeter-based inflation models are working with most, but not all, of the summit instrument coverage, and the forecasted episode 54 window of August 24th to August 28th reflects the accuracy of the current reduced network rather than the full instrumentation capability that was available before the outages. For residents of the Big Island and the hundreds of thousands of visitors who travel to Hawaiʻi Volcanoes National Park each year hoping to witness the volcanic activity, the implications of the current eruption pattern are both practical and profound. The summit area of Kilauea, including the caldera rim surrounding Halemaʻumaʻu, has been closed to public access since late 2007, a closure that was driven by the collapse events that opened the active lava lake in the summit at that time, and that has remained in place through all of the eruption activity since. The lava fountaining episodes of the current series are therefore not directly witnessed by park visitors, who observe the glow of the eruptions from the Kilauea overlook and other designated viewing areas at safe distances from the caldera rim. But the VOG that the eruption produces travels downwind without geographic respect for park boundaries, and during active fountaining episodes, air quality across the Kona coast, the Hilo area, and other populated parts of the island can reach levels that health officials recommend limiting outdoor activity for sensitive groups. The Hawaiian Volcano Observatory has been monitoring Kilauea continuously since 1912, making it one of the longest-running dedicated volcano monitoring programs in the world. Over that century-plus of observations, scientists have documented eruptions ranging from gentle, effusive lava flows that advance slowly enough for residents to observe from a safe distance to explosive eruptions in 1924 that blasted rocks across the caldera and created ashfall visible across the island chain. The range of behavior that Kilauea is capable of producing within its eruptive history spans many orders of magnitude, and the current episodic summit eruption represents one point on that spectrum, rather than the full extent of what the volcanic system can do. Whether the current eruption eventually migrates into the rift zones, as the 2018 eruption did following a period of summit activity, is a question the observatory monitors with every tiltmeter reading, every gas measurement, and every earthquake catalog it produces. What can be said with certainty today, August 22nd, 2026, is that Kilauea is in an unusually sustained and evolving phase of eruptive activity. 53 completed lava fountaining episodes over 20 months, a new west vent that appeared for the first time during episode 53, an earthquake swarm in the southwest rift zone the day before that episode began, a south vent that has become less dominant relative to the north vent in recent episodes, an inflation model pointing to episode 54 between 2 and 6 days from now, and an observatory monitoring network that has been partially degraded by storm impacts even as it continues to track the signals that matter most for public safety. The volcano that drives the island of Hawaiʻi is not settling down. It is changing episode by episode, vent by vent, microradians of tilt at a time. The science is watching every measurement. The question that the instruments will answer in the coming days is exactly what episode 54 looks like, and whether the west vent that opened its eyes in episode 53 is ready to fully wake up